Hi everybody, we've covered the independent samples t equation, how to calculate it, how to interpret it. Now I think it's important that we also cover the dependent samples t-test and equation and how to calculate all of that. So in this particular video, I'll just walk you through the hypotheses, the null and alternative hypotheses, and the equation itself in principle, and then we'll actually practice calculating it and interpreting in future videos. Okay, so once again, the independent samples t-test assumes that there are two independent samples that do not influence each other in any way whatsoever. However, the dependent samples test assumes that the two groups do influence each other. In fact, the best way to do that, or at least have some relation to each other, I should say, the best way to do that, of course, is to have the same people in both groups. Okay, for example, you might have a diet pill or something, and you test people's weight before they start taking the diet pill. Then you give them the diet pill, and I don't know, for 6 months or whatever you decide, and then afterwards you weigh them again. So it's literally the same the same people at two different times. This is sometimes also called the related samples test. So a dependent samples test or related samples test are the same thing. Okay, it's a very important test, very powerful. If you're able to actually conduct and design a dependent samples test, it makes a lot of sense because you're literally controlling for lots of external variables that you can't control for otherwise, because it's the same people, right? So if you've got the same person in group 1 and 2, you're controlling for any differences in IQ that may have been there, any genetic differences, age-related differences, all sorts of other things, because they don't change at all. It's the same exact person. All of their background, all of their history, for example. So it's a very powerful test and very, very preferential. Powerful meaning statistically powerful, quite literally. So we covered statistical power in a previous video. Okay, now let's get into the assumptions of the dependent samples test. So you recall that the independent samples test assumes some things to be true, right? We had a whole video about that. Similarly, the dependent samples test also assumes things to be true. And if these are not true, you may be making a mistake. You may be increasing your chances of committing an error, and we don't want to do that. So you as the researcher need to ensure these things are true. First of all, the dependent samples test assumes that there's normal distribution on the dependent variable for both groups, okay? So in other words, they're relatively bell-shaped on that dependent variable, and of course the dependent variable does need to be continuous. And secondly, it assumes independence within the groups, okay? Now, again, as the independent samples t-test assumed that the groups were independent of each other entirely, in this case, we assume that the people within a single group don't influence each other's scores. Okay, now, for example, let's imagine that I go down the street and I say to a group of people, hey, would you all mind telling me about your political, I don't know, your political opinions? And if they're all in a group together and I'm having them just answer questions one to another, the real problem here is that they're listening to each other's answers and they're probably not telling me exactly what they think. They're telling me what they hope people want to hear, for example. And so that would be a terrible design because I'm not actually getting people's real feelings. I'm getting, they're influencing each other. It might be one issue here that would affect the independence within groups, okay? So in other words, it assumes that we're getting a single score from every individual. We're not getting multiple scores from multiple individuals, and they're not influencing each other's scores even within each group. And again, just like the independent samples t-test, the dependent samples t-test is also robust to these violations. So if there is a problem here where you didn't quite achieve independence within the groups, it's still probably going to make the correct call. However, at a bare minimum, if you do violate one of these assumptions, please tell your audience so that they're aware of that also, and they can kind of take it with a grain of salt, take your results with a grain of salt. Now, the null hypothesis and alternative hypothesis are very important, of course, for a dependent samples group. They're a little bit different from an independent samples group, and so make sure that you're saying the correct thing. Now, again, just like always, we assume that the independent variable has no effect on the dependent variable. That is our default hypothesis. Now, in this case, if we believe that there's been no change between time 1 and 2, if we're doing a paired samples t-test, or a repeated measures t-test in that particular case, we would expect to see no mean difference on our dependent variable because our influence didn't do anything. Our independent variable didn't make any change. Okay, so we shouldn't expect anything to change if our default hypothesis is true. Now, what that looks like in symbols is something like this, We've got the default hypothesis, or H sub O, which actually is 0. And then this is the mean difference, or the expected mean difference, okay? The mean difference is, of course, a parameter. We expect a mean difference is 0. We expect that we had no influence whatsoever in between the two times that we measured these people, or in between these two groups that we think are somehow related to one another. Yeah, so that's the mean difference right there. Now, the alternative hypothesis looks like this. That, of course, means that we did have some influence on our dependent variable due to our independent variable. Okay, so if we did make some influence, that means that we expect now a mean difference that is different from time 1, or time 2 is different from time 1, for example. Okay, so that could look like this. We might not expect a difference in one specific direction. For example, maybe we think mean 1 and mean 2 will just be different. We don't know which one will be higher or lower than the other. We could also specify the direction in which we expect to see the difference. For example, if I'm doing a weight loss pill, then I expect people will be heavier on average before my intervention, before the pill, and lighter after the pill. So if I'm measuring them in weight, I would expect a larger number minus a smaller number, and a mean difference therefore that is positive or greater than 0. So in that kind of case, I might want to specify that I expect to find a mean difference larger than 0 and ignore anything that is smaller than 0. That, of course, would use a one-tailed test criterion. Again, if you're not sure on the one-tailed, two-tailed test, we did an entire lesson on that previously, so go take a look at that. Now let's take a look at the equation and get familiar with that. So here's the equation. It looks like kind of a lot going on, and there kind of is, but it's really not that difficult, and we'll practice with it, of course, in the next video, as I stated. So let's get familiar with this just a little bit. All right, every time you see one of these capital italicized D's, what that means is the difference, right? It stands for the difference in the scores from, for example, time 1 and time 2, or in some cases, group 1 and group 2. Okay, so in other words, this is just taking the sum of the differences, the difference scores, and this is the total number of times we have a difference score, okay? You could also think of it as sort of the number of times we have, or the number of paired observations of the variable we have. So there's always somebody in group 1 that is paired with, in some way, somebody in group 2. So this is how many pairings we have. So think about that. Let's say we have 7 people in group 1. We would have to pair them with 7 people in group 2. So it's not 7 plus 7 is 14 is our observations. It's actually 7 paired observations. So n sub d would be only 7 observations. Here, of course, yeah, I don't know. Yeah, here, of course, is the squared differences and then summed up. So we'll cover all that and how to calculate that later. All right. One important thing here is, of course, this guy, the mean differences that we saw in the null hypothesis. Okay, that is virtually always going to be 0, and so it's you almost don't even need to include it in the equation. However, it's important to remember that because there may be some rare circumstances under which it would not be 0. You wouldn't expect the mean difference to be 0. Let me just sort of think about that. Like, let's say that you measured them at time 1. And then at time 2, you gave them a shorter survey or something, like, or you use some psychological measure at time 1, and then at time 2 you used a shorter measure. Well, now you would expect the score then to drop by, let's say it's 3 questions or something. You would expect it to drop by 3 questions, and you might be making a mistake by treating it as if you wouldn't expect any difference at all. So if that mean measure actually would drop, you would want to include that in your null hypothesis, that you would see a drop of 3 points and no more than that. So that's the only kind of thing. Now, it's a little beyond what we're messing with here, because virtually in all circumstances, you will just treat that as 0. So don't worry about that too much unless you're doing something fancy here. Okay, and I already talked about that n sub d. Okay, good. Okay, so in some way, it's kind of like this. It's really just the average differences between the groups, or the variation we can account for with our independent variable. And then down here it's almost the same thing as the standard deviation of the differences between groups. Actually, but because of this little guy here, this little n sub d that we divide it by, we never did that before. Because that's there, that actually makes this the standard error of the mean differences. That's a pretty technical term, so at this point you can just make sure you do it. If you're not even sure what to call it, that's fine. And you can think of it essentially as the differences that we cannot account for, however. So the ratio, our t equation, or our t statistic is a ratio of these differences that we can't account for to the differences that we can't account for. All right. Okay, so as I said, we're going to compute one using some made-up data in the next video. So seeing some raw scores, you can see how we actually get to an equation, get to a solution, a statistic. And then after that, I'll show you how to find the degrees of freedom and to interpret everything we've done. Then, of course, after that, I'll have another video about effect size and confidence intervals. I think I'll combine those into one video. So I will see you then. Thank you.